Okay, we will now discuss the celebrated Noether's theorem. And this was the theorem that was established in 1918 by Noether. So in 1918, Noether established a theorem which was the first formal link between symmetries and conservation laws. In particular, she established a link between invariance in time and conservation of energy. So this is essentially then Noether's theorem. And it's a theorem that was established in 1918. It's 102 years old. And the theorem goes like this. I'm going to use this proof, but please follow it line by line as I go through it. First of all, suppose we had a Lagrangian L of some differential equation, i.e. EL equals 0 gives you the differential equation. Suppose we determine the Noether's symmetries as we did in the previous example. So with a gauge F. So if X here is xi d by dx plus eta dy is a Noether symmetry coming from the invariance of the integral of L, that means following this Lagrangian L, then with the corresponding gauge F, remember every Noether symmetry with gauge has a function F associated with it, then Noether's theorem essentially says that a first integral of that corresponding Euler-Lagrange differential equation is given by I. I is L times xi coming from the symmetry, plus this important factor here in brackets, eta minus y dashed xi, multiplied by dl dy dash, that's a partial derivative of the Lagrangian with respect to y dashed, minus the gauge term f, which is a function of x and y. So in this particular proof of theorem, we're actually given the form of I, we just need to prove that. Well, to prove that, we need to show, by definition of a conservation law, that di dx is equal to 0, not trivially, but on the equation, on the differential equation. That's important. So this has to be established on the differential equation. What is the differential equation in this case? Well, you've got the Lagrangian, then curly E on L equal to 0 is the differential equation. So we know for a fact that curly E on L equals 0. That's the differential equation. You need to keep that in mind. Don't lose track of that. I'll just remove that to give myself some space. Right. And EL equals 0 means that the differential equation is in fact that. Right, let's start. Right there. There's di dx. Di dx means differentiate the function I in the theorem totally with respect to x. So essentially there's lots of quotient rules, etc., product rules, etc. So if you go back to the theorem up there, the form of I up there, oh dear, changed all the colors. There's I there. Then di dx is, well, applying the product rule on L times xi, it's the derivative of L times xi, derivative of L with respect to x multiplied by xi, then leaving L as it is, differentiating xi, so that's dxi dx, total derivative. Then if we go to that term there, the product is the bracket and dl dy dashed. This is the total derivative of that bracket. The bracket has an eta, so there's an that there. Inside the bracket we have the term y dash xi, which is another two terms, so it's a product rule. So if you differentiate y dashed xi, you get y dash the derivative of xi minus the derivative of y dashed is y double dashed times xi. product rule, leaving dl dy dashed as it is this time. Right, then leaving the bracket as it is and totally differentiating the second term being dl dy dashed. And then lastly differentiating the f in that equation of I, df dx. So essentially we were looking at that form of I and differentiating I totally with respect to x, lots of product rules within product rules. Right, you may recall that the total derivative operator from before is given by that. So I'm going to expand the total derivative operator up to a convenient form. If the function it is operating on is up to first order derivative, then we just need the first three terms. If the function is dependent only on x and y, we only need the first two terms, etc., etc. Right, now expanding. Therefore, going back to di dx, if you expand dl dx in terms of partial derivatives, since L is a function of x, y dashed, you expand dl dx, you get that. The xi stays as d's. We're leaving the L times dxi dx as it is. So let's just leave that as it is. Then in the second term, I've left the d eta dx minus y dash dxi dx minus y double dash. This is y double dash up there. That's y double dash xi left as it is, multiplied by dl dy dashed. That's left as it is. Then we've got, following from the previous step, eta minus y dashed xi. This is left as it is, so we don't need that, minus df dx. So the only thing that was done was that little step in expanding the total derivative of L with respect to x in terms of its partial derivatives. That's the only thing that's been done from the previous to this step. Right, now what? You notice that in this step, y double dashed dl dy dash times xi comes up twice, one of the positive and one of the negative, so this term will cancel with this term after you multiply those two round brackets. Okay, you have to do that multiplication, and then these two terms will cancel off. Right, so going from this step to the next step, then the cancellation is done, and you will notice that the only thing that I've done after the cancellation is to add and subtract the same term there, eta dl dy minus eta dl dy. I've added and subtracted that, and you'll see exactly why that is so. Here's the reason. If you take dl dx times xi, if you take dl dy times eta d x minus y dash dxi dx, so that's its whole bracket. So you're taking this term, I should in fact circle the whole thing. If you take that, and this term that we've included now, if you take these three terms, right, since, first of all, notice that this term here is eta 1. And there's a bit of a thing that is not showing here. This is dl dy dashed there. So you got dl dx times xi. You got dl dy times eta, which is circle. Then you got dl dy dashed times eta 1. That bracket is eta 1. You add these three terms, you end up with x1 operating on L. Here is x1, if you recall from before. So that term, that whole term there, so this term is after the product, of course. And this term gives us x1L. I'm collecting terms now. Right. This term I've just repeated. Here it is. The df dx I've just repeated. Here it is. Okay. And then I've just included other terms. For example, you will notice that this term here I've reproduced there, and then I collected remaining terms. The remaining terms are, in the previous step, this minus eta dl dy and this product here. Okay, so I collect the remaining terms and I end up with this term here. Okay, right. Now, how did you calculate Noether symmetries in the previous examples, previous two lectures? We said we let x1 on L plus L dxi dx equal df dx, which means this thing, if x is a Noether symmetry, this thing is in fact equal to 0. Okay? And hence I've put in that 0 there. The two terms that remain have a common factor of eta minus y dashed xi. There's eta minus y dash xi, and those are the remaining terms coming from that. So that we have this factor included there, but since we have an Euler-Lagrange equation, this is the Euler operator on L, and EL, curly E on L is equal to 0. Hence, that's 0 there. And when all this simplifies, di dx equals 0. Therefore, di dx equals 0 on this equation here. So we have a first integral, a conservation law, given by I equal to L xi, etc. If x, capital X, is a Noether symmetry with gauge f, and we have all this from a Lagrangian of the differential equation capital L. We will do an example on this next time, showing that one of those previous examples in which we calculated a Noether symmetry corresponding gauge term for a given Lagrangian. We'll construct a first integral based on one of those 5 cases. Just take one case. If there are 5 Noether symmetries, there'll be 5 such first integrals corresponding to that, using this theorem. We'll take one of those in the set of 5 and show that we end up with an I, and prove in fact that di dx equals 0 is your equation.